Today we're going to talk about Reynolds transport theorem. So Reynolds transport theorem is basically a general conservation law that you can use to derive conservation of mass and conservation of momentum. So we're going to see where the conservation of momentum equation came from today. Our learning objective is just to derive this conservation law so you can see it. There's not going to be any sort of long answer questions on your final, things like that about this. So don't worry too much about, I guess, the derivation. I'll probably ask questions maybe in a short answer sort of format about what this theorem is, what the different terms are, just to test your understanding of the theorem. I'm not going to ask you to apply this to do some horrible triple integral that'll take you 45 minutes or something like that. There's kind of an interesting thing though. So this Reynolds transport theorem comes from one of Reynolds, I guess, is one of his last papers. So from 1903. So this was after he did his obviously very famous Reynolds number stuff. Um, he he wrote this thing called the Submechanics of the Universe, and it's about 300 pages long. Um, and it's I guess it's a really interesting thing. So the the this 300-page document opens up by saying that by this research it is shown that there is one and only one conceivable purely mechanical system capable of accounting for all the physical evidence as we know it in the universe. So if that sounds like a hot take, it really is a hot take. Um, Especially because in the next paragraph, Reynolds kind of says that the entire universe is basically a continuum approximation. So it says the entire universe is basically an arrangement of spherical grains um, that kind of affect each other's motion. And it constitutes the entire universe, everything constitutes an elastic medium with 6 axes of elasticity symmetrically placed. So basically, a lot of the stuff in this 300-page document is wrong, unfortunately. It just goes to show that, so if you find fluids unintuitive, that's okay, because Reynolds is obviously the most famous person to have researched fluids. He has the Reynolds number named after him, which is the most important non-dimensional quantity in fluids. Not everyone is perfect. So I haven't read all 300 pages, but I have read that I guess the theories that he talks about, again, this was 1903, so we didn't know that much about physics. For example, this Reynolds theory of the universe allows for faster than the speed of light travel. It allows for anti-gravity. It allows for infinite energy sources, all things which over 100 years later we know are not possible. So anyways, the whole thing is it was a bit of a hot take, but this transport theorem, this generic transport theorem that he derived in this paper is actually still really useful in fluids. So that's what we're going to look at today. I won't be going through the more hot take side of this paper. Okay. So the laws of physics are usually written from a Lagrangian perspective. So for example, F equals ma is about kind of a point mass. We're following this point mass. The summation of forces on our point mass at any point is equal to the mass times acceleration. That's a Lagrangian perspective. But we know in fluids, we often use an Eulerian perspective. So what Reynolds transport theorem does is it allows us to convert Lagrangian conservation law into an Eulerian control volume perspective. So this control volume analysis we've been doing is kind of by definition an Eulerian point of view. So we're going to watch this fixed point in space, this fixed sort of piping segment in space, and track the momentum coming in and out of it. That's how we determine the forces, say, on that piping body. That's an Eulerian perspective. So I guess what sort of thing do we expect to appear when we talk about conversion between a Lagrangian and Eulerian perspective? We talked about this in the first half of the course. Material derivative, that's what I heard. Yes, that's good. So we're going to see basically what this material derivative kind of looks like with a bunch of integrals in it, which is lovely. Okay, so we're going to consider, to derive kind of the Reynolds transport theorem, we're going to consider a simple flow through a converging nozzle. So we're going to watch a fixed region of space like this. That's our control volume. Again, our flow is kind of going through this. So our control masses that we're going to track, so the sort of systems that we're going to track are going to be these kind of chunks of fluid going through our converging section. So the red blocks are our control masses. So that's an Eulerian perspective. So we're going to track a certain volume of fluid as it moves throughout space. So control mass. And when you watch those control masses, you're by definition using a Lagrangian point of view. We're going to analyze two very specific moments in time of this system. So we're going to consider a time 0 here. And at time 0, our control mass is perfectly all within our control volume. So our control mass and our control volume are the same size. And at a time t plus delta t, our control mass has moved a little bit. So our control mass has moved. We're going to call this, how about t here? And the second time is t plus delta t, so small delta. So just to make the colors clear, this is a fixed CV. The red is a moving control mass. So at time t, what we're going to do is say our mass at time t, our control mass, is equal to our control volume mass. So the total mass of fluid in our control volume is just equal to the mass of our control mass, because our control mass is the exact same shape as our control volume. At time t plus delta t, control mass's mass at time t plus delta t we're going to have a couple of different regions here. So we're going to have this blue area. I'm going to call that kind of region 1. This orange area, I'll call that region 2. This is just basic, I guess, geometry. So our mass there at time t plus delta t, the mass of the entire red box, is m CV t plus delta t minus m1, where again m1 is the mass in this region, this blue region, plus that m2. So I don't think that's too confusing, but I'm just going to explain this again to be clear. So our objective is to keep tracking the mass of our control mass, which is the red region. So at time t is a very specific time. They perfectly coincide. So it's the same amount of mass in our point mass that's in our control volume. After a certain amount of time, the control mass has moved a little bit. So the mass of that control mass is going to be equal to the green mass, the green box, minus whatever's in the blue region, plus whatever's in this orange region. So that's M1 and M2. Do you have a question?
I was just curious as how if it's like a fixed CV, how can it be a function of a change in time, the mass?
So a fixed CV is like an Eulerian point of view. So you can have an unsteady Eulerian flow field, right? And this problem would probably be steady, but that's basically going to go away. But you can have an unsteady Eulerian flow field, right? Any other questions? Okay. So let's now calculate the rate of change. So the rate of change here is we're going to do basically delta m over delta t. So that's m t plus delta t minus m of t over the time step delta t. Okay. So the change in mass is going to be the mass at time t plus delta t. Basically, the change in mass is going to be this minus this. So that's the mass. This whole term is just the mass at time t. Plus, sorry, t plus delta t. Minus the original mass t. All that over delta t. So all I did was I'm just doing the delta in mass. So this minus this. Okay, so we're going to take a limit here. Delta t going to 0. The other thing is yeah, okay, I'll just take this limit. So I'm going to use capital D here because we're going to get basically something that looks like the material derivative. dm by dt equals partial m cv partial t. So this limit as this would be as delta t goes to this limit here. So I'm just doing this term is, does anyone have a guess at what this is? So It's a mass over a time. It's a mass flow rate, right? So that's the instantaneous mass flow rate, m dot 2. It's the same thing for m dot 1. So our material derivative is equal to this minus, so the m dot in is our blue component, plus m dot out. Okay. So our Eulerian control volume masses combine into this partial derivative term. Then in the limit, these m2 over t plus delta t over delta t, those each go to the mass flow rate. So what we see is that the change in mass of our Lagrangian thing we're following is going to be that local rate of change of the mass in the control volume minus the mass that's entered the control volume plus the mass that's gone out of that control volume. Okay, so what for mass specifically? If I didn't give you this, what would you say that the left-hand side is equal to? Yep. 0, because that's just conservation of mass. If you follow the same mass, the mass can't change by definition of conservation of mass. So that equals 0 is by conservation of mass. Okay. We're also going to make these substitutions. Here's where the integrals enter. The mass of our control volume, we've learned, is the volume integral of density. And this, say m dot out. Okay, I'll say this m dot out minus m dot in. M dot out minus n dot in is just simply the net mass flux. We know how to calculate that now. It's that area integral, the net mass flux. So that's rho v dot n dA. So we're trying to generalize this now to not just our very simple control volume in a converging section. Okay, so let's substitute. We're going to substitute these two things into our kind of very intuitive equation here. And we're going to get partial by partial t that volume integral plus this area integral is equal to 0. So this is the equation that I've given before, and we've shown this before, which is just conservation of mass. Yep. So we derive conservation of mass for this control volume. And this kind of looks like a material derivative. So basically the material derivative of the mass in our control mass should be 0. We shouldn't be able to change the mass of our control mass. That means you have that sort of local rate of change, plus this is more of like a flux. So this isn't exactly equal to the material derivative because that's kind of defined for a small fluid parcel, but it's similar to a material derivative when you think about it, in that you have that local rate of change plus the fluxes, so plus some sort of spatial difference. So this derivation can be extended to an arbitrary extensive property. So maybe in a thermal course or something like that. Have you guys seen extensive intensive properties before? Okay, good. So a reminder, extensive properties, they change with the amount of mass. So for example, mass, of course, changes with the amount of mass. 1/2 mv squared. The momentum, intensive, it changes with, let's say, the type of mass. So for example, density, pressure, velocity. So material properties or these other quantities divided by mass become intensive properties. So in general, the intensive property is equal to the extensive property divided by mass. So I'm not going to repeat this derivation. If you want me to repeat it for you, no thanks. But you can repeat this derivation. So we've done an extensive property here, which is mass. We've considered the time rate of change of mass, so the sort of mCv, and the flux of mass, we've set that equal to 0. You can basically substitute, instead of mass, another extensive property. In fact, a generic extensive property that doesn't really matter what it is. So we'll call that n, which is extensive. And we're going to have a corresponding variable called eta, which is an intensive property. Where eta is n per unit mass. So our Reynolds transport theorem in words says, again, this is, I'll keep it in red just as a reminder. So that's our kind of material derivative. So this is following a control mass. The total time rate of change of n inside our control mass is going to be equal to the rate of change of n within, say, the control volume. Within the CV, plus the net flow rate of n out of the control volume. So in math, this is this is the Reynolds transport theorem. So partial by partial t of a volume integral of rho eta dv plus this area integral rho eta v dot n hat dA. So that's Reynolds transport theorem. So any questions so far? Like I said, we can derive conservation of mass and conservation of momentum immediately from this. There are other things you can derive, but in this course, we're really worried about conservation of mass and conservation of momentum. So there is a way to get back to the Navier-Stokes equations from Reynolds transport theorem. So we derived it one way. There are many ways to get to the Navier-Stokes equations. Another common way, which you might see in fluids too, is using the Reynolds transport theorem. Okay. So as a reminder, in this equation, we get to pick n, and we also, based on knowledge of the problem, we have to pick dn by dt if n is a vector, the above is a vector equation. Okay, so we're going to do conservation of mass. So in conservation of mass, we're conserving mass. So we say n is equal to m. That means eta equals mass per unit mass, which is always 1. We also know, as I mentioned during the derivation, that the time rate of change of mass following a control mass should be 0. So we can't change the mass. With these, if you substitute these three things into this above, you get partial by partial t, volume integral. So eta is just 1. So that's how you get conservation of mass using the Reynolds transport theorem. Okay. Now we'll do conservation of momentum. So I did the easy one. Maybe you can help me with the hard one. So what is n for conservation of momentum? What is the extensive property that defines momentum? Take a guess. Yep. The velocity. Okay, so that is velocity an extensive or intensive property? Intensive, right? So that's our eta. But what is the extensive property? Momentum, right? It's not a trick question, despite being framed like it was. So our extensive property for conservation of momentum is momentum of a control mass, remember? So that's mv. Our intensive property, mv over m, which is equal to v. So I have another question. So what about dn by dt? I said we get to pick this, right? So what do we expect the total change of momentum, the total time rate of change of momentum of a control mass to equal? So we got 0. Yeah, I think you're about to get it. What do you expect the total time rate of change of momentum something to equal? 0. Okay, that's a good guess. It's not 0. An impulse, right? So it's just the sum of forces on the control mass, right? So dmv by dt equals summation of forces is just Newton's second law. So this is just Newton's second law for our control mass, which says that the time rate of change momentum is equal to the sum of forces, aka ma. So with these, we get the conservation of momentum that I showed before. So we've been using this equation. We've been using an easier form of this equation for the last couple of lectures, but there it is derived using Reynolds transport theorem. So all you have to know is that your total time rate of change of momentum will be equal to the sum of forces, and you can derive the conservation of momentum for a control mass. Any questions about this? Okay. So that's basically the end of content. I'm going to do some kind of menti stuff now on test our understanding of this. So the first question I'm asking, the term on the right-hand side there, is that a scalar or a vector? Okay. Seen a very, very strong opinion here that this is a scalar, which is good. So this is a scalar. This, um, I'm not going to ask you that because I think I ask you that later in this. Okay. So yes, it is a scalar. Um, if, by the way, if you get one of these wrong and you want to like just ask me why it's wrong, feel free. I know it's kind of intimidating if you're the one person who said vector, but that's okay. So this is a scalar. This one appears in our conservation of mass equation, which is a scalar equation. What about this term? Okay, it looks like a very even split. So basically, I'm asking if you evaluate this, I'm not asking you to evaluate this. If you were to evaluate this, would you expect a number or would you expect a vector? Um, this is a scalar, okay? So this also appears in the conservation of mass equation. There are vectors in this, but this is a dot product. So remember, the dot product reduces two vectors into a scalar. So this is just rho times a number. So this is a scalar. Are there any questions about that? I know it's confusing because there's vectors, but it's not. This whole operation is a scalar. What about this term? Okay. Yes, you're all right. It is a vector. So it's a vector because we kind of have a leftover vector in this integrand. So in the other one I just showed, we had vectors in here, but the dot product of those vectors reduces them to scalars, and then we integrate them. In this one, we just have a leftover vector, which we're doing. So we're doing kind of a volume integral. Actually, we're doing the partial derivative of a volume integral of a scalar times a vector. Lovely, right? Lovely. Okay. What about this term now? Okay. Yes. It seems like basically everyone answered that this was a vector. Yes, this is a vector. So again, scalar, scalar, but we have a leftover vector. So we're doing an area integral of a scalar times a vector times a scalar. Um, yeah, which is a vector. Okay. The equation there is the Reynolds transport theorem for a generic intensive property. So I'm asking you, oh, sorry, this term, I should say this equation. Is this equation a vector equation, a scalar equation, or it depends? So does someone who said it depends want to explain? I mean, we're going to be, you guys are going to be engineers, right? So it's, the answer is always it depends. Maybe why? So he put his hand up first. Yeah. Because you haven't chosen what eta is, right? So what if you chose eta to be a scalar? What would this be? Scalar. And a vector? Be a vector, right? Exactly. So this equation, like for example, the material derivative, it doesn't change the rank of what we put into it. So by rank, I mean scalar, vector, and it gets above that, but I'm not going to go there. Any questions about that? Yep.
So if you put a tensor in there, would it also work?
Yes, this would be a tensor. So you would have a tensor is sort of um, this is not within the scope of fluids one. This will not be on your exam. But tensor is kind of a generic geometric quantity. So a scalar is a zeroth order tensor. A vector is a first order tensor. A matrix is a second order tensor. So a tensor is, we would use in fluids, we would say scalars, vectors, and then go up to tensors. So it would be like a matrix. So you would get a time rate of change of each of your matrix elements out of this, and you would have to do a volume integral of basically a matrix times this thing. But tensors, they go higher order than matrices. So your matrices is kind of a 2D one, a second rank one, and then you can get 3D ones, like fourth order tensors. For example, like Einstein's relativity equation, I can't remember what order that is, but that's kind of getting to tensors. Yep. Do you have a question?
Oh, I was just asking like what happens.
What happens after? It just keeps going. It just keeps going until like you basically run out of actual physical things these 20-dimensional tensors actually represent. In fluids, it kind of ends at second order tensors. I didn't. Okay, okay, here we go. So in your own words, what is this term here? This appears in the Reynolds transport theorem. You're not allowed to put down what I just put, even though I know many of you will. Try and describe this in your own words. Some volume thingy. Unfortunately, it disappeared, but this is the first term in the Reynolds transport theorem. So this is the volume integral term. Some of these are creative. Um, yeah, so it's a volume. I would not say you have a good understanding of what this term represents based on this whole. Um, so this one is probably the closest. It's how eta changes with time in the control volume. It's the closest, but since it's a volume integral of eta, and eta is per unit mass, so this is a volume integral of density times eta. Eta is per unit mass. So this is actually how n changes with time in the control volume, how the extensive property changes. So very close. I think probably the most creative one is this one. That one wins the creative. Okay. Sorry, we did talk about limits. We did. I apologize.